Hello. Hope all of you are doing very well, and I welcome you to a close look at the strong and weak acids. You take a strong acid, well, take hydrochloric acid. The hydrochloric acid would completely break down to give H plus and Cl minus ions in water. This ionization is 100%. So if I take say zero point 0.1 molar hydrochloric acid, the solution would definitely have zero point 0.1 moles of H plus ions in 1 liter as given by hydrochloric acid. If I take zero point 0.1 molar H2SO4 in aqueous solution, obviously each mole of H2SO4 dissociates almost completely to give double the number of moles of H plus ions. So 0.1 mole of H2SO4 solution would give 0.2 moles of H plus ions in aqueous solutions. So that is the fate of strong acids. Similarly, a strong base, if I take 0.3 moles of NaOH in water, it completely dissociates to give as many moles of OH minus ions. If I take zero point 0.2 moles of barium hydroxide, its formula is BaOH taken 2 times. This zero point 0.2 moles of barium hydroxide would completely dissociate in aqueous solution to give us this 0.4 moles of OH minus ions. Now, having said and done all this, if I take a weak acid, what happens to it? That is our question. A weak acid would completely, it may dissolve, but it won't dissociate in aqueous solution. Why it won't dissociate? Because it is a weak acid. What happens to a weak acid? It dissociates to a small extent. To what extent? Let us say it dissociates to an extent of alpha. So if I take acetic acid, whose concentration is C in a 1 liter water, the number of moles of acetic acid that dissociates can be represented by C alpha. So if I start with C, the solution will be left out with C minus C alpha moles of acetic acid. And the solution will also have C alpha moles of H plus and C alpha moles of acetate ion. I don't care for acetate ion anyway. So the H plus ion concentration is given by C alpha. What is C alpha? Sorry, excuse me. C alpha is the concentration of H plus ions. It is not C. C alpha is much less than C. Okay. Now, at equilibrium, can you see? Anyway, you don't consider water because water is in large excess. The change in concentration of water we can ignore. Therefore, technically, if you look at the aqueous solution of acetic acid, I start with C moles. I am left out with C minus C alpha moles of acetic acid, which is not dissociated. C alpha moles of H plus ions and C alpha moles of acetate ions. In water, H plus ion cannot exist separately. H plus ion exists as H3O plus hydroxonium ion. Always any acid will release H plus. H plus exists in water as only H3O plus. In fact, water pulls away the H plus by making a dative bond and it generates H3O plus. It is the water that is responsible for separation of H plus ions from acetic acid. Anyway, at the moment we are looking at, if I take acetic acid, whose concentration is C, at equilibrium I can have C minus C alpha acetic acid moles, C alpha H plus and C alpha acetate ion. What is the equilibrium constant expression? Ka acid dissociation constant is equal to concentration of product ions product divided by concentration of the reactant. Concentration of H plus ion into concentration of acetate ion divided by concentration of acetic acid. C alpha into C alpha divided by C minus C alpha. You can simply see it as Ka is equal to C alpha square by 1 minus alpha. That is the expression for Ka. Weak acid dissociation constant Ka is equal to C alpha square by 1 minus alpha. Alpha is very, very small. So 1 minus alpha is almost same as 1. Therefore, the denominator 1 minus alpha can be seen as 1 approximately. Therefore, Ka is equal to C alpha square. Please remember, keep it in the upper right of your brain. Ka is equal to C alpha square is true for weak acids. What are weak acids? Acetic acid, tartaric acid, citric acid, even hypophosphorus acid. So many weak acids. Further, the formula applicable is Ka is equal to C alpha square by 1 minus alpha. Generally, alpha is very small. Ka is equal to C alpha square. Similarly, for weak bases like ammonium hydroxide, calcium hydroxide, magnesium hydroxide, for weak bases, a similar relation, they don't dissociate completely to give OH minus ions. So the base dissociation constant Kb is equal to C alpha square by 1 minus alpha. You can always neglect alpha in the denominator. You can say Kb is equal to C alpha square. Two important consequences, please. H plus of weak acid is equal to C alpha. Please write down. Take time to write down. H plus is equal to C alpha. C alpha is also equal to, please write down, square root of Ka into C. H plus ion concentration is equal to square root of Ka into C for weak acid. Similarly, for a weak base, OH minus is equal to C alpha, which is equal to square root of Kb into C. Strong acid, strong base, H plus ion concentration is corresponding to the concentration of acid you have taken. Always don't forget, you have to see H2SO4 0.1 molar means H plus ion, each H2SO4 gives 2 H plus. So molarity of the acid into number of H plus ions given by each molecule, that is 2. Number of H plus ions given by each molecule of acid, number of OH minus ions given by each molecule of base is called as its N factor, let us say. So for H2SO4 0.5 molar, H plus ion concentration is 0.5 into 2. 2 is N factor. This is an idea. And also if you take water, pure water also dissociates, but one molecule dissociates out of millions of water molecules. I can say out of 10 to the power 7 water molecules, 10 to the power 7 means that is 10 millions. Out of 10 millions water molecules, is it 10 millions? Yeah. Out of 10 millions water molecules, one molecule breaks down to give H plus into OH minus. This is called autoprotolysis, self-dissociation of water. And the number of H plus given by water is equal to number of OH minus ions. As far as pure water is concerned, H plus is equal to OH minus, H3O plus is equal to OH minus. As long as H plus is equal to OH minus, water is pure and neutral. Okay. Now what happens? At 25 degrees centigrade, the water dissociates to an extent of 1 molecule out of 10 to the power 7. The solution gives 10 to the power minus 7 H plus ions, that is the number of moles, 10 to the power minus 7 moles per liter. And also pure water at 25 degrees centigrade gives 10 to the power minus 7 moles per liter of OH minus ions. So if I multiply the concentration H plus with OH minus, I get what is called water ionic product represented by Kw, which is equal to 10 to the power minus 7 and 10 to the power minus 7. That is 10 to the power minus 14. Water's ionic product value at 25 degrees centigrade is 10 to the power minus 14. If I am rising temperature, originally at 25, out of 1 million water molecules, 1 is dissociating. If I raise the temperature, then the number of molecules dissociating may increase. Then water's ionic product value also increases. It may go like 10 to the power minus 14, which changes to 10 to the power minus 13.5, 10 to the power minus 13, so on. If it changes, it means H plus ion concentration is increasing, OH minus ion concentration is also increasing. As far as pure water is concerned, at 25 degrees centigrade, that is 298 K moles of per liter of H plus, 10 to the power minus 7 moles per liter of OH minus. If I add H plus, this concentration of H plus will increase, automatically OH minus ion concentration will decrease, but the value always remains 10 to the power minus 14 if temperature is 25. That's all for now. Thank you.